Hey everyone, coming to you, not exactly live, from Alderdice, for now at least. Welcome to our classroom. Okay, so now that you know how to take the derivatives of logs, we are going to take a look at something called logarithmic differentiation, which sounds like so much fun. It involves the rules of logs, which hopefully you remember. If you recall at the beginning of the year when we took a calculus readiness test, that's one of the things that came up. They're kind of a big deal. Everybody tends to learn them and then swiftly forget them, but they are a big deal. And if you look at my screen here, the three big rules, these are the ones that you need, okay? That if you have inside of a log, if you're taking the log of a product, that you are able to rewrite that as the ln of those two products separately. That if you have a quotient, you're able to write them separately, but it's a subtraction. Notice it's numerator minus denominator. And the big one, that if you have a power, you're able to bring that power down as a multiplier. I know that may seem strange to you that those rules are true, but they really do work. For example, if you have something like, I'm going to do the log in a base 10 because it's easier to talk about, but if you have something like a log of 100, right, I could easily rewrite that as the log of 10 squared because that's what 100 is. Okay? And then if you have a squared, you can bring the 2 down. So 2 log of 10, and we know that the log of 10 is 1 because that's, what do I have to raise 10 to get a 10? 1. So guess what? It's 2. This question originally was asking, if you have a log in a base 10 of 100, the question is 10 to the what gives me 100? Our answer is 2. Okay. So if you remember just in general what a log is, you can kind of have simple examples of why those work, but in the end you really just have to believe that they do. I love the rules of logs. They are among my favorites. I think they're magical. Okay. So if we were in class together, I would have had you warm up by doing some rewrites using rules of logs. So we're going to do that together here. So if you have the natural log of 3x to the 5th, the first thing that we are able to do. Now you might say, well, why would you though? And in this section, we're going to have a reason, right? But you can bring the 5 down, right? So I can write this as 5 times the natural log of 3x. Okay. I also can, if I choose to, since this is a product, break up this log. Now I want to point out to you though that that 5 applies to both the 3 and the x, so we have to be careful there. If we're going to break this up as a product, I need to make sure I leave the 5 applying to both. Like that. Okay. Now you may be saying to yourself, and you probably said this in algebra 2 as well, why would I do that? Why would you take something beautiful like this and break it into something like this? But what you will see in this section is that we absolutely need to do that in order to get the job done. Okay. This one, again, I have an exponent. Notice that my exponent applies to this whole quantity, so I'm able to bring it down. Okay. What I am not able to do in this example, though, is break this natural log apart like I broke it up here. We have a rule that says that if you have multiplication, you may break it into addition. We do not have any such rule for addition. I believe I talked to you about this at the beginning of the year a bit, but I have a way, when I teach exponents to my, dare I say, my little ones, we have a superhero called P-Man, and P-Man stands for power, multiply, add, and nothing. Okay. And P-Man tells you what to do with your exponents. So I tell them, for example, if you have a power to a power, so if you have x to the 3rd and it's being raised to the 5th, you multiply your exponents. If you are multiplying, so if you have x to the 3rd times x to the 5th, you add your exponents. It's x to the 8th. If you are adding, if you have x to the 3rd plus x to the 5th, you can't do anything. Right? And we're pretty good with the rules of exponents. I want to point out to you that P-Man applies to logs as well, because as you may remember, logs and exponents are. Okay. P-man is basically these rules as well. Look, if you have a power in a log, you may bring it down as a multiplier. That's this rule. If you have a multiplication in a log, you may break it apart as an addition. That's this rule, right? Division becomes subtraction because they're just opposite operations. And if you have an addition in a log, you may not do anything with it. You may not break it apart. We don't have a rule for that. Okay? So if you have trouble remembering the rules of logs, just remember that you already know the rules of exponents and they're kind of the same. Right? You can call on P-man the superhero if you need him. All right, so let's talk a little bit about logarithmic differentiation, shall we? Okay. So far, we have two rules for when we have a situation where there's a base and there's an exponent. The first rule is the one we learned very early on. This is the power rule, right? Okay, so in other words, I have a variable in my base, so something like, oh, I don't know, x, and I have a constant up top, so something like maybe 7. And we know how to take the derivative of that. Just use our power rule, 7x to the 6th, no big deal. Just recently, we learned how to deal with the exact opposite of that. So I have a constant in the base, and my variable is up top. Okay. In that case, that's a different rule, right? This is the exponential rule, where I have to say, okay, well, that's going to be 7 to the x, and then I need to tack on the ln of 7. So I have two rules already to deal with when I have a quantity being raised to the power. The way we choose which rule we're going to use is by looking at where the variable is. If the variable is in the base, then we're going to use the original power rule. If the variable is in the exponent, we're going to use the exponential rule. Well, what if there's a variable in both places? Now this is the simplest one I could think of. Okay. The power rule only works if there's a constant in the base. The exponential rule only works if there's a constant in the exponent. You can't apply either rules to this. Good news. We have tricks. And they're called the rules of logs. Dun, dun, dun. I love them. Okay, so check this out. This is what we call logarithmic differentiation, and it's not nearly as scary as it sounds. Okay. What we do when we have logarithmic differentiation, first we move my floating head so that you can actually see the problem. Okay. What we do when we have logarithmic differentiation is we apply two rules. The first rule being, I do what I want as long as I do it to both sides. The second rule being that I have this little friend called the log. I like to use the natural log, that lets me do stuff that I can't do when there's not a log around. So for example, oh, I don't know, if you have a log, you can take something like an exponent and make it no longer be an exponent. Because if you're working with logs, we have this rule that says that you can take your exponent and multiply it down in front. So if you have a log, for example, if you have something like the natural, if you have something like the natural log of x to the 5th, I can take this power and turn it into not a power anymore. Turn it into a product. So what we're going to do for logarithmic differentiation is we're going to take advantage of both of those rules. Okay. We're going to say, well, if I had a log, I could take this power and multiply it down and create a product here. Oh, if only I had a log. Enter the other rule of math. I do what I want, as long as I do it to both sides. So my first step in logarithmic differentiation is simply going to be to take the log of both sides of the equation. As long as you do it to both sides, you haven't done anything. It's fine. Keep your seesaw balanced. You can add 5 to both sides, you can subtract 100, you can multiply by 27, you can take the log. Right, now, I said natural log only because we know that when we use the natural log, it gets us out of, in our derivatives, doing things like writing the ln of the base. And so it's just kind of one more thing to not have to do. So I always use the natural log. There's absolutely no reason you have to use the natural log. You can use the log in a base 10. You can use the log in a base pi. It doesn't matter as long as you do it to both sides. Just know that if you're using a log in a base other than e, then when you're doing your derivatives, you're going to have to be tacking on the natural log of the base. And that's just something I don't want to have to do. So the first thing we always do is take the natural log of both sides. So I'm literally going to rewrite my equation as the ln of y on one side and the ln of x to the x on the other side. Step one. Okay. Now, why did I do that? I did it so I could get rid of this exponent. I don't know how to take the derivative of an exponent or of a variable raised to a variable. I do, however, know how to take the derivative of two variable things that are being multiplied. So my next trick is going to be to rewrite this thing using the rules of logs. So on the left, I don't have much to do. It's still just the ln of y. On the right, though, I can now take this x and bring it down as a multiplier. So this is going to become x times the ln of x. From here, there's nothing new. All it is implicit differentiation. Okay? So my last step is going to be to use implicit differentiation. So logarithmic differentiation is simply recognizing that you have this situation where you have a variable to a variable. We don't have a rule for that. And getting yourself out of that situation by using some stuff that we do have, something we do know. One, we know we can take the log of both sides. And two, we know that once you do that, you can eliminate that whole variable to a variable situation. Once you've eliminated it, we're back to implicit differentiation. So I'm going to do my differentiation on both sides. So the derivative of the natural log of y is going to be 1 over y dy dx. On this side, I have a product. So I'm going to have x times the derivative of the natural log of x, which is 1 over x dx dx, plus the natural log of x times 1, which is the derivative of x, dx dx. Again, you may be completely over writing dx dx by now, and that's fine if you are. So I'm now down to 1 over y dy dx equals, this is x over x, and then here I have the ln of x. Now remember, when it comes to implicit differentiation, we always have to solve for dy dx. So I have dy dx is equal to this whole quantity times y. Now listen, one last thing you have to do here. You may remember from implicit differentiation me telling you that if they give you an equation and it is written y in terms of x, then you are expected to give an answer y in terms of x. If they give you an equation and it's all jumbled up, then it's okay to return a jumbled up answer. Same thing goes here. You were given an equation y in terms of x. Our answer needs to be y in terms of x. So the fact that we have this y sitting here is kind of a no-no, right? But it's a real easy fix because we know what y is equal to. So literally all we have to do is rewrite this, 1 plus the ln of x, and replace that y with what we know it to be equal to, which is x to the x. And there we have it. There's our derivative. So again, logarithmic differentiation sounds like a lot. I know it does. I hear myself saying it and I'm like, ugh, that sounds like something we don't want to do. But it really isn't, it isn't a lot. It's almost nothing new, right? It's implicit differentiation. Our only job in logarithmic is to get our equation from a space where we cannot use logarithmic differentiation, or I'm sorry, where we cannot use implicit to a place where we can. And we do that again using those two steps. Taking the log of both sides so that we can implement the rules of logs and get that exponent out of there. And that's it. All right, let's do a couple of examples. Oh, hello. Let's move my face again. Okay. All right. So in this case, I have y equals 2x to the sine 4x. So again, you may notice, look, variable in the base, variable in the exponent. It's screaming for logarithmic. So the first thing I'm going to do is take the natural log of both sides. The ln of y equals the ln of 2x to the sine 4x. Now, I implore you to be careful here, and always. This exponent applies to the x. It does not apply to the 2. It's important to recognize. If they wanted it to apply to the 2, there would have been parentheses here. There aren't parentheses there, which means that sine 4x is an exponent for 2, for x, and only x. Which means that you cannot immediately take this sine 4x and multiply it down, because if you do that, you're applying it to the 2 as well. You're saying this was the exponent to both the 2 and the x, therefore I'm multiplying it down out front. So in this case, and in cases like it, before you go multiplying this down, you got to split it up, because otherwise, when you multiply this sine 4x down, you're applying it to the 2 as well. So before I do any bringing down of exponents, I'm going to first break this up using my rule for products. I have the natural log of 2 plus the natural log of x sine 4x. Now, I have a situation where I can bring it down. So now, and again, as you start doing this on your own, you may bring that down in one step, and that's fine. Get better and better at this. So now I have the sine of 4x, I'm bringing down front, times the ln of x. Okay. Logarithmic part is done. Now I'm just ready to do implicit differentiation. I've got it rewritten in a way that I can apply implicit differentiation. You're going to notice these are kind of cool too, because they're not even hard implicit differentiation questions. It's always the same over here. The natural log of y is 1 over y dy dx. Please don't forget about that part, right? You can't just write like, oh, y prime equals. No, you're taking the derivative of y. It's 1 over y, or the natural log of y. It's 1 over y dy dx. Okay, over here, I have the ln of 2. The derivative of that is just 0. It's fantastic. And then here I have product. So let's handle it. The sine of 4x times the derivative of the natural log of x, which is 1 over x dx dx, plus the natural log of x times the sine of 4x, so cosine of 4x times 4, don't forget to chain rule, dx dx. Okay, so dx dx, see you later, whatever. I have over here, if I clean it up a little bit, a sine 4x over x. And then here I have a 4 ln of x cosine of 4x. Just cleaning it up a little bit. All I have to do to finish it off is take this y and multiply it to the other side. So my final answer is going to be all of this, sine 4x over x plus 4 natural log of x cosine 4x times y. I'm going to bring this, multiply it over. But instead of writing y, I'm going to write what I know y is equal to. I'm going to write times 2x to the sine 4x. I'm done. Looks like a lot, but it's mostly implicit. All of the calculus here is implicit differentiation. The stuff in the beginning, the green here, it's all algebra. I know, I'm talking to you, Shirley. It's all algebra. Everybody's favorite. Okay. About this one. Give it a shot. Okay. Again, I've got a variable expression raised to a variable expression. This 5x squared applies to this, so I can immediately bring it down. It's not like there's a 2 out front or something like that. So I'm going to have the natural, the natural log of y equals the natural log of the tangent x raised to 5x squared. Use my rules of logs. I'm going to bring my 5x squared down. Okay. Again, the algebra is done. I took the natural log. I brought my exponent down. Now I'm ready to do calculus. Now it's implicit time. So 1 over y dy dx. Can't stress this enough. That derivative is going to be the same every single time. And over here, we're going to have a product. If you don't have a product, something's wrong because you were supposed to have brought down an exponent. It's the whole point of doing logarithmic. Unless you're just doing it for fun. Just like implicit, if you want to do every problem from now until the end of time using logarithmic differentiation, do it. If you love the rules of log so much that you want to take the natural log of every function ever and do logarithmic forever, do it. I support you in your ventures. Okay. But as it is, I only do it if I have to, even though I do other things. All right, let's do a product. So I have 5x squared. The derivative of the natural log of tangent x would be 1 over tangent x. Derivative of tangent, which is our friend secant squared, dx dx. Plus the natural log of tangent x times the derivative of 5x squared, which is 10x dx dx. All right, so if we clean it up a little bit, I've got 5x squared secant squared x over tangent x plus 10x ln of tangent x. All right, last thing to do, again, don't forget this part. In the answer point, you're obviously going to lose points if you don't bring the y over. But you will also lose points if you write it as a y and you don't replace it. So, here's my pen. I've got my whole thing here. 5x squared secant squared x over tangent x plus 10x natural log of tangent x times, I didn't leave myself any space, the tangent x of 5x squared. I'm so sorry, I didn't leave any space. I'm just replacing, I'm writing a times y here, right? And I'm replacing my y with what I know it to be equal to, which is the tangent x raised to the 5x squared. Okay. Okay. Another example. Okay, let's do it. Natural log of y equals the natural log of x plus 5 to the 3x to the 4th minus 2. I'm going to be really careful when I bring this down, because if I'm not careful, I'm going to lose this quantity. So I'm going to make sure that I put that in parentheses. Don't write it in parentheses. You're going to end up having 3x to the 4th minus 2 ln x plus 5. That's not the same thing. All right, so let's take our derivative. I did my algebra derivative time. 1 over y dy dx equals, there's my product sitting there waiting for me. So I have 3x to the 4th minus 2. The derivative of the natural log of x plus 5 is 1 over x plus 5 dx dx. Plus natural log of x plus 5 times the derivative of 3x to the 4th, which is a nice neat 12x to the 3rd. Again, dx dx. So if I'm cleaning this up, I have 3x to the 4th minus 2 over x plus 5. This is just a 1. And over here I have 12x cubed natural log of x plus 5. And I need to multiply my y to the other side. So all of that times the y that we have to bring over, and y is this. Ta-da! Okay. So I have one more for you, and instead of having to read my chicken scratch writing, oh crap, I really just did that all for no reason. Well, you don't have to read my chicken scratch writing. There it is in beautiful rainbow colors, the solution that I lost track of my own self with all the steps. So again, you may want to, I don't know if you want to take a picture of this for your reference, but I used to, when we were together, I would put this on the board for you to check yourself. But again, it kind of shows it in every detail without my awful handwriting. All right, let me know what questions you have on this, and we will talk soon.